Hi everybody. I want to go over the first part of experiment 1 calculations for your report in this video. So what I want to do is share my screen, and here's number 1, 2, and 3 for that report. In 1, it asks you to calculate the concentration of bleach in units of molarity. I'm going to assume that my bleach was 5.132% by mass. Yours was 4 point, I don't know what, but you have it because you wrote it down from the bottle. And what that means, that percentage means that in my case, there was 5.132 grams of NaOCl, the bleach, per 100 grams of solution. They give you a density, so you can convert that from grams to milliliters. Then you convert from milliliters to liters because molarity is in moles per liter. And then that leaves me only converting the grams of bleach to moles of bleach using the molar mass, 74.44. And that comes out to be about 0.745 molar. All right. The next question is I have to calculate the initial concentrations of the dye and the bleach for run A, knowing the dilution law, which I have written right here. Molarity dilute times the volume dilute equals the molarity concentrated times the volume concentrated. So if I rearrange this equation to solve for molarity dilute, it equals the concentrated times the volume of the concentrated over the volume of the dilute, which I put in here for the dye. This was off the bottle. We took 20 mils, diluted it to 21. The bleach, I just calculated above. For my case, your case is going to be different. We took 1 mil of that, divided and divide by 21 because that's the total volume. So this is the initial concentration of bleach. Also, you're going to have to explain, it says justify assuming the concentration of bleach is much greater than the dye. Explain why it's important. So first of all, you want to say it is 0.0355 is much greater than 7.6 times 10 to the minus 6. And it's important because when you want to use the method of isolation, you're trying to isolate the effect, in this case, of the concentration of dye on the rate of the reaction. So how do you do that? You try to fix it so the concentration of the bleach doesn't change. And you do that by making a lot more concentration of bleach than the dye. So in effect, as the reaction proceeds, the concentration of dye is changing from this 7.62 times 10 to the minus 6 molar to 0 compared to the bleach, which is, for all intent and purposes, pretty much constant. Because if this is a one-to-one relationship for the reaction stoichiometry, then if I subtract from the bleach that has a concentration of 0.035 molar, if I subtract 7.62 times 10 to the minus 6, hey, it's pretty much 0.0355 molar, you know, it's not going to change. So it's constant. So that concentration's constant, and that's important for using the method of isolation as explained, or as you should explain in question 3. Use equations 13 and 14 and rewrite it in terms of the bleach and dye. So here I have equation 13 from the background. It says that the rate should equal this K0 times e to the y. Now for the background, they say, okay, we're going to be using this reaction E plus B. So the overall equation for this reaction should look like this guy right up here. Rate equals k times b to the x times e to the y. Now, if we make b really great compared to E, then it's pretty much constant, and we can incorporate that constant effect of B right into the rate constant K and just call it K0. And then once you do that, then you can use the graphical method and plot the concentration of dye versus time, or 1 over the concentration of dye versus time, or the log of the concentration of dye versus time, to see if you get a linear function. Because if one of those turned out to be linear, then that corresponds with the integrated rate law for 0th order or first order or second order, and then you can say that that dependency for 0, first, or second must be true. It's holding. So you're going to need to read the method of isolation and explain that, and then put in dye for B and E, or E, and put in bleach for the other one. So I think you should be able to figure that out, which one is constant and which one is varying during this experiment. All right, I want to do a new share now, and I want to share this sample data that I have from a student in my class on Monday. Okay, so what I want to do is clear this, because I'm going to show you how to generate that. So in class, you took timing and absorption data, all right? And this one corresponds to run A. One of my students gave me these results. Up here, I have Beer's law written out. So this pertains to the directions for writing up your lab number 4. So we did 1 through 3 already, so now we're doing 4, which asks us to use Beer's law, which says that the absorbance equals the molar absorptivity E times B, the cell length, which is 1 centimeters in your case, because you used the cuvette that was 1 centimeter long, or wide, I should say, times the concentration. So the first thing they want you to do is calculate that molar absorptivity, E, knowing that the pure dye had this concentration, 8 times 10 to the minus 6 molar. So what I did with Excel is I just put in this cell equals H5, which is the absorbance, experimental absorbance that I found for pure dye. All right, I just picked it. It's in the ballpark. You'll put your value in. And you can do this if you have Excel. If not, you're going to have to do it by hand. You're going to have to calculate this E as the absorbance 0.77 divided by this pure concentration C. And so you get this value when you put it into Excel. All right, moving right along, once we have E, then you can go back and calculate the concentration of all your values using the molar absorptivity divided into the absorbance. So here I have it in Excel. It makes it really easy. I'm going to put equals, and as soon as you put equals, Excel knows you're going to be putting in a formula. So that formula is going to be the absorption, which is right here. And I'm going to divide that by, let's see, I'm going to have to divide that by the molar absorptivity, which is right over here. Now, I could just return, and it gives me the concentration, knowing that the absorbance is 0.58 in that case. But I want to use Excel feature where I turn this into this little darkened black cross and fill down. But I don't want it to change this K5 value. See this block K5, that's the value that it's taking. I don't want it to change it. So I'm going to change this from a relative definition to a global definition by inserting a $sign there. So you see I still get the same answer, but now when I fill down, it's not going to change that molar absorptivity. And I can do that for all of these, and it just fills it right out really nice, and I don't have to do it by hand. And you can do the same for the log of the concentration. So this would be equals ln, and then I need a parentheses right there, and then I go to this concentration, and boom, and then I could just go ahead and fill that down, and that gives me all my values and so forth. And I can do that again for the last one. It would be 1 divided by this concentration. I'm sorry, I have to put in an equal sign, or Excel doesn't know. Equals 1 divided by this concentration. Enter. And then again, I could fill it all the way down. And then I'm ready to make the plots for this as prescribed in that question 4. So for this one, the first thing we can do is plot the time versus concentration to see what we get. So there's my concentration. I'm sorry, that's my time. I hit control, and then I can click this in Excel, and then I can go to insert scatter plot, and there I have my concentration versus time. You see its curvature, and so that's no good. I'm going to try to do the next plot, which is the log of the concentration versus time. So what I do is I click outside of this, or it'll get replaced. I can select those times again, and this time I'll do control and then select the log of the concentration, and I'll insert a scatter plot again. And now you can see this is much better for linearity. And I can do the same for 1 over concentration versus time. I'll let you play with that, but you're going to have to fit these to equations aligned to prove that one's more linear than the other. So I'm going to add a trend line, and I'm going to tell Excel to display the equation and the r squared. Now that's really nice if you have Excel. If you don't, then you're just going to have to eyeball it and say, hey, this is obviously curving, as opposed to the other, this one, which is linear, and the other one, 1 over concentration versus time, is also going to be curvature. But if you have Excel, then you're lucky, and you can display the equation and the r square, and you can see that the r square for the log of the concentration versus time is 0.9988. It's almost 1, so the closer it is to 1, the more linear your fit is. So that r square value tells me that the log of the concentration versus time is a better fit to a line than the concentration versus time. Okay, so I think that ought to get you started for that part of the question. Now, I have this slide, which I have all of the the runs done here. And so I went back and I filled in for run B and C, just like I showed you how to do for A. Put in that raw data of absorbance, and then using the absorptivity and Beer's law, convert to concentration. But for runs B and C, you only have to generate the log of the concentration, not the 1 over, because the 1 over didn't come out linear, and so that means that it's not going to come out linear for the other ones, and the only one that's going to come out linear is the log of the concentration versus time, and that's the only one you have to plot for the other guys. So I have those 3 plots down here for run A, B, and C. They're all the log of the concentration versus time. And notice, before I upload it for my report, I make sure that they have a title, and I make sure that the axes are also labeled with their units. In this case, the y-axis doesn't have any. And notice that I changed the equation of the line that Excel gave me to illustrate what's actually being plotted. So I changed the y to ln of concentration, and I put units on my slope, and I know that the units for the slope has to be 1 over s because it's rise over run. Also notice that that's consistent with the equation, because x I had to take out and put in time and its units, seconds. So the seconds will cancel out, and I get an equation that's consistent in units. So y is unitless, the slope times x is unitless, and the intercept is unitless. So it's consistent. And that's going to be uploaded into your report for part of number 4 and 5. Now, 6 says that you want to, let me see, yeah. So 6, we're gonna look at this next part that I prepared, table 6. So in number 6, it asks you to prepare a table with your results. So here's the table 6 that I have, runs A, B, and C. This is the slope is related to K. If you look at the integrated rate law for first order, it says the log of the concentration equals minus KT plus the log of the initial concentration. So that means that the slope M has to equal minus K. And if you look back there, the slope of plot A is minus 0.0068, so K has to be plus 0.0068. And the same thing with the slope of B and C. Also in this table 6, I added the initial concentrations of the dye using the dilution law, and the bleach for my case using the dilution law for each one of those runs. So that pretty much rounds out the assignment for number 6. I have a table 6, and I have it appropriately titled with the temperature, and that needs to be uploaded as part of your report. Now, question 7 uses the information to table 6 to not only calculate the power dependence of bleach on the rate, but also give the overall rate law. So if we look back at the reaction that you guys performed, you took dye and you added the bleach and it gave you some product. So we know as soon as we see that the form of the rate law is going to look something like this, where we have the rate equals K times the concentration of dye to the X, which we now know is first order because of its association with the integrated rate law for first order, and using the graphical method, which is just a no-brainer method, which says that if you plot all these different functions, you can see which one's trending linearly and then associate it with the integrated rate law, which tells you how that concentration should behave depending on which order it is. All right, so because of the method of isolation, we have this definition of K0, and we know that the concentration of bleach is constant for each run, but we can compare those Ks from one run to the other, and they want you to do that for A and B. So if I take the ratio of A, which is defined like this, Ka has to equal this K back here times the concentration of bleach in run A to the Y, right? And I divide that by Kb, which has a similar definition, that should look like this. And so when I do the division of Ka of Kb, I get 2.344 from my results. Here's the concentration in A over B. That ratio comes to 2, and it's to the y power. So I have to solve this for y, and I do using the law of logs. And I get y equals 1.22. 1.2. So that tells me that the overall rate equation looks like this. And that caps it for question 7, and that does it for this segment. I'll be doing another video, I suppose, for part B. Thanks for listening, and hopefully this helps.